Hi there once again and welcome back. In this video we'll start our fourth topic, which is the load analysis. Now before we can size up the structural member or the mechanical components, we need to have a solid foundation about the forces that acts on the system. Okay, so we need to know how to analyze the forces that's acting on the system. So this topic is actually where we get to start to do a lot of computations. Okay, so for the content of my presentation, first we'll talk about loads, and then we'll talk about equilibrium equations and even the equations of motions, and also we'll talk about the joints and supports, determinacy, load path analysis, and internal forces. Okay, so these topics or you have already encountered this in probably in statics and also dynamics and strength of materials, and even in our previous course in structural engineering or AB structures engineering. But right here we'll be discussing this, but the orientation is toward the mechanical design. Okay, so for example, in terms of joints and supports, then we'll have examples like probably more in 3D supports for the bearings, for example. Okay, because I really believe that when we need to determine the radial loads and let's say the thrust load for the bearings, what we need is the three-dimensional analysis. Okay, rather than just simply doing the simply supports like pin and roller supports. Okay, so that's why it's really necessary to go through this 3D analysis. Okay, and we'll also talk about the determinacy and the load path analysis and internal forces. But again, as I've said, that all these topics, they'll be, or the examples that will be given are more on mechanical systems. All right, now let's start with our first topic here, which is the loads. So load analysis is a fundamental considerations in machinery design, and not just in machinery design, even in structures. That's very fundamental. And the size of the structural members or the mechanical components, for example, the shafts, the beams, the brackets, and many other parts or assemblies, the size of the structural members are determined depending upon the load that they will carry, because we all know that if the load if the load is greater than the capacity of the member, and the capacity of the member is also given by the or expressed in terms of the size or the geometry of the material and even the properties of the material, is that if the load is greater than the capacity, then the material will fail. So that's why in mechanical design or in design in general, we need to have this capacity aspects as greater than the loads. Otherwise, it will fail. Okay, so right here we have here a shaft assembly. So we have a shaft, and the shaft is being supported by the bearings. So here's the bearings and another bearings, and the shaft carries a gear. So we have a spur gear right here, and then another spur gear. So probably let's say this is the input gear. So this gear is what's driving the shaft, and this one will be the output gear. Okay, so we have this force that's being exerted in this gear, so that force will be coming from the other gear. Okay, and that concentrated force or this point load is being induced by the mating gear. Okay, so because gears, they transmit forces through the meshing of the teeth. Okay, so example, this is the teeth of first, I mean, of this gear, and then another gear is this one. So the force is being transferred uh, through the contact of the gear teeth. Okay, so that's external force. Okay, so because of the external force that's being induced in our mechanical system, then that's gonna develop support reactions. Okay, so in the bearings, it's a type of supports that allows rotation. Okay, allows rotation in this, let's say in this x-axis, but it does not allow movement in the z and the y-axis. Okay, so because of these external forces, then support reactions develops. Okay, so this one develops. This one is a support reaction, and right here is also support reactions. Okay, and also this driven gear, since it is also meshed with the other gear, then there's gonna be a reaction from the other gear. Okay, so again, because of these external loads, then there develops a support reactions, and because of these support reactions, there actually develops internal load. Let's say in the shaft. So if we make a section cut or section plane, then if we check this, then what we will see inside is the stresses. And in this example, we see this torsional stress, torsional shear stress distribution. Okay, so that depends upon the analysis. Like for example, if we want to include the weight of let's say the weight of the gear or the weight of the shaft, then there's gonna be also shear stress and also bending moments. Okay, so from that internal loads, we can obtain the stress, and we can also obtain the strains if we want. And recall that stresses, they're related to the forces, whereas strains, they're related to the deformations. Okay, so in analysis, how do we work, or how do we compute the forces and the moments? And by the way, when I say loads, I mean forces and moments. And moments, these are just simply forces that causes rotations. So in analysis, we need to have an idealization. So for idealizing the load, we can idealize the load as concentrated. So it can be concentrated load, point loads, or concentrated moments. Okay, so again, if you recall that this concentrated moments, the unit is, or for moments, the unit is Newton meter, and this one, the unit is Newton for the metric systems, or pounds for English system, and this one is pound inch. And just remember that the distance here is the perpendicular distance. Okay, so although this moment has the same units as the energy, but this distance is perpendicular to the force, right? So for example, I have this member right here, and this is my point of or my center of rotation or center of moment, and I apply a load right here. So because I have an eccentricity, that distance is actually the moment arm. So because of this eccentricity, then the result would be rotation of the body, or of the material. Okay, so concentrated loads or concentrated moments. And example of the concentrated loads are the meshing of teeth of gears, or the belt tensions in pulley drives, or even in chain drives. So we can idealize them as concentrated loads, and also support reactions, torques and shafts, or things like that. And another idealization is the line loads. So what this means is that it is a distributed load throughout a length. So the unit of this, if it's a line load, that's Newton per meter. For the concentrated loads, for the force, it's just Newton. Okay, so for the line loads, these are typical for for example, the weight of the shaft or the weight of the beam or the load on bearings when considering the load variations. Although for support reactions, right here, actually that depends upon the analysis. So if you have let's say a non-regular load distribution, then of course the effect is that you would have a more complex mathematics. Okay, so that's the line loads, and for surface loads, the unit is Newton meter squared. Okay, so that means that the forces or the loads are acting on an area. Okay, so over an area, so that's why the unit is Newton per meter squared. So where do we see this these surface loads? That's typical idealization for, let's say, wind loads on fins of heat exchangers. Also the loads on beams, like for example we have beams and silos. Then since it's actually an area right here, so if we check the top view, since we have, let's say, a grain or a granular material right here, then of course there's going to be forces, a force distribution. And since this is a wall, then that's an area. Okay, another example is the buoyant forces on floaters. Okay, so it's just area. Okay, so again, the loads can be idealized as concentrated loads, as line loads, or surface loads. Okay, so here I have included here the concept of tributary area or tributary width. We have encountered this already in our course in AB structures engineering, but this one I really think that this is helpful when we adopt this area. I mean when we adopt this concept in mechanical designs, because sometimes this simplifies the analysis. Okay, so just a review, the tributary area or tributary width is the loaded portion that contributes to the amount of load a member will carry with respect to the other members. Okay, so again, it's the loaded portion that contributes to the amount of load a member will carry with respect to the other members. Okay, so for example, I have here a subsoiler. So a subsoiler is a type of implement that that kills the soil if the soil is hard. So because we need to have or we need to perform tillage before we can do the planting operation. So in some types of soils that it's really hard to break, then this implement is being used. Okay, so for example, this subsoiler, this by the way, when we say implement, it's being pulled by a tractor. Okay, so for example, this subsoiler is attached to this beam right here, and there's another subsoiler right here, and then another subsoiler, so it's being spaced at some distance. Okay, so my question is, how do we know how much load will it get? Okay, so how do we know? So the concept of tributary area is useful for this analysis. Okay, so for example, imagine that there's a soil. This subsoiler is submerged in a soil. So if it's submerged in a soil, then if we look at this view, if we look at the top view right here, so imagine that this one, the surroundings right here, they are soil. Okay, so this subsoiler, the motion of subsoiler is towards let's say to the right, to the left. Okay, so because of this, then because there's a presence of soil, then of course it's gonna encounter reactions or something like a reaction from the soil. Okay, so if we how do we convert this area All right, so how do we convert this area to a line load? Okay, so that's what this tributary area this is what the tributary area do. Okay, so it can we can sometimes this is tributary width. Okay, so from this area, from this loaded area, we can convert this into an equivalent line loads. Okay, so once we have these equivalent line loads, then we can analyze this um, using the principles of statics. Okay, so this is three-dimensional, but we can simplify this into something like a two-dimensional analysis. Alright, another example is the flatbed dryer. So for example, it is flatbed dryer. By the way, this flatbed dryer is used in or is found in processing operations. So after you do the harvesting, of course, the moisture content of the let's say of the grain, the moisture content of the grain is still high. So you cannot store a grain that has a high moisture content simply because it will promote growth. Promote molds and deterioration, and also it would lessen the storage life. Okay, so that's why it has to undergo drying. Okay, so that you can store it. You can so that you can store the grains longer. Okay, so one equipment for drying is the flatbed dryers. Yeah, and this flatbed dryer is basically a bean. So it's a bean, and if we draw the side view, okay, so this is the supply blower or supply air. Okay, so from a heat source, let's say we have a furnace or something like a diesel burner or things like that. Okay, so this is a blower. This will introduce the hot air. Okay, so hot air will enter the plenum chamber. Okay, so right here, and there's actually a layer right here. Okay, so that's a perforated sheets. So right here, that's the perforated sheets, and this is where you you store or this is where you place the grains for drying. Okay, so after some time, because you are subjecting the grains uh, to a hot air, then of course there will be some evaporations of the moisture. Okay, so the principle is that hot air enters this, and then because this is a perforated sheets, so that means it's a let's say it's a sheet that has perforations or holes. Okay, so it will exit right here, and because it is hot, then of course there some moisture will be evaporated. Okay, so how do you this actually this sheet right here, there must be some structural supports, because how would it be possible to be able to carry this grain bed and the framings without without these supports? Okay, so if the support is just simply the ends, then of course, well, what you need is a very rigid or very stiff material, flexural member right here. So that's why there must be some supports right here, and let's say we have this kind of supports, right? Okay, at some or space at some distance. So from this space to that space, something like a bay distance. Okay, so how do we know, or how do we compute, or how do we analyze the loads that will be carried by this member or by this assembly? Okay, so again, the concept of tributary area or the concept of tributary width is very useful for this analysis. So for example, I will sum up the loadings from the framings, okay, from the frames plus the grain. Okay, so since it's a distributed area, then I can multiply that distributed area with this width right here. So what will happen is that it's something like I'm shrinking this width down to a line right here. Okay, so this is gonna be my equivalent line load. Okay, so again, because this is two-dimensional, and we already know how to compute this two-dimensional or these line loads. Okay, another example is the belt conveyor. So we already learned in our previous course in process equipment design that a belt is a type of conveyor equipment that, for example, this is our material to be conveyed right here. So it rests on the belt. It is stationary. I mean, it is relatively stationary. It just rests on the belt, and this belt is moving, right? And because the belt, it has I mean, it's not possible to have a let's say to have a longer distance, let's say between pulleys. It's simply because there's gonna be deflection from the belt. So that's why we include or we provide idlers, and this one is trough idlers having this trough shapes. Okay, so how do we know, or how do we compute the loadings of this let's say of this one idler? So we use again the concept of tributary width. Okay, so all this area right here, the weights, or the weight that's acting on this area, that's in kilonewton per meter squared, and we multiply that to this width right here. So what we get is a line load, kilonewton per meter. So we can analyze this as what we already know, right? Okay, and one last example is the hand pushed wheel mounted power sprayer. So for example, right here, this is our hand pushed wheel mounted power sprayer. So this power sprayer, it has a chemical tank, and it also has some hose assembly, and it also has engines and pumps. Okay, and what if we want to compute the forces that will act on this wheel, right? So what's going to be the force? Okay, so instead of I think instead if instead of going through the load path, some simplifications is that to use the concept of tributary area. Although you can also do 3D static analysis if you want, like for example the weight of the engine plus the weight of this pump plus the weight of this chemical tank plus the weight of this hose and things like that. I just convert this to a surface load. Okay, so once I have the surface load right here, it's like acting on this base or on this base frame. Okay, so once I have this, I can compute, or I can do 3D static analysis if I want to be able to solve this these forces. Okay, however, it's also possible to have this, to adopt this tributary area concept. Okay, so it's like how would I know how much concentrated loads that this point will carry? Is simply by dividing this, dividing this halfway and dividing this distance halfway. Okay, so this area right here, that's the area, or that's the loaded area that will contribute to the loading of this point right here. Okay, so that's just a one way of simplifications. And of course, if you want, we can also consider the motion, and then let's say the friction and things like that, which just complicates the analysis. And if you have the means to solve that, then that's fine. But if not, then I think simplification sometimes is okay. Alright, loads can also be classified as either static or dynamics, and what that means is simply if the load remains constant with time, then that's static, or um, if the load varies with time, then that's dynamic loadings. Okay, so what that means is that I mean the static loadings sometimes, even though it varies with time, but if the variation is just slow, or the gradual increase of loads is just slow, then we can sometimes consider that as a static loading. For example, by the way, the most common example of these static loadings are, for example, the beam that rests on a column, for example. Okay, so that's the loading. Let's say the weight of the beam. That's constant with time. Okay, so that's the typical example. But right here, here is an example of let's say a gradual increase, like for example the hydraulic jack. Okay, so let's say this hydraulic jack is carrying a a car, for example. Okay, so because of this action right here, then there's gonna be a force that push this, let's say this body right here, or this material right here is being pushed up. Okay, so even though there's changes in the force, but the application of the force, it's just gradual, so it's still considered as a or it can be analyzed as a static loading. Okay, and for the dynamic loadings, we have two types. We have impact loadings or fatigue loadings, and the difference between impact and fatigue is that for impact, it can be described as a something like a sudden increase. Okay, so take note of the word. That's a sudden increase of the force or the load. Like for example, this one, the pile hammer. Okay, so it's being the pile, the force right here, it's actually an impact loading. Okay, and I mean for this fatigue loadings, this type of loading, this is described as repeated loadings. Okay, repeated loadings. This one is sudden increase or sudden loads. Another example of this sudden loads is, for example, in the threshing cylinder, and if there are let's say foreign materials or hard foreign materials, like for example stones, then it can cause impact on the peg tooth of the threshing cylinders. Okay, so that impact loads, it's actually much larger than the static loadings. Okay, so if the part is designed only for static loadings, then that's gonna be a problem if we don't consider the impact loadings. Although in practice, probably sometimes this impact or this aspect of impact is just being considered altogether in the use of safety factors. Okay, anyway, that depends upon the designer and the governing codes, if there are available codes, as long as in the end the machine must be functioning, and not just functioning but also must be safe. Okay, so for fatigue loadings, we have described that it's a repeated loadings. So example of that repeated loadings is the connecting rod of the engine. So right here, here's a picture of an engine, and this is the piston, this is the connecting rod, and right here is the crankshaft. So recall that this piston actually undergoes a linear motion, so it goes up and goes down, and this crankshaft, this converts this linear motion into a rotating motion, or in a rotational motion. Okay, so you would notice that this connecting rod is being subjected to once it's going, let's say once it goes up or once it goes down. So sometimes it experiences compression, and in another another time it experience tension. Okay, so this is an example of repeated loadings, and there are we have we have a topic for this fatigue loading computations. I mean, we'll also do computations for fatigue loadings, but the um, the main point right there is that um, we don't just consider the static loadings. Okay, so we also have to take into account the fatigue loadings and the impact loadings, if or whenever possible, because for example we have a steel right here. Let's say a steel specimen. So we have learned already that when you subject this steel in compression, or let's say tension. Okay, so once we subject this steel specimen in tension, we we already know this stress strain diagram. Okay, but and in this stress strain diagram we have obtained the yield strength, right? The yield strength, or the Fy, and also the ultimate strength. However, when the material, or when this specimen is subjected to fatigue loadings, the strength would be much lower. So for example, for steel, if we have a 250 megapascal yield strength for steel, for fatigue loadings, probably it would be like I don't know, maybe 60%, or uh, maybe 150 megapascals. Okay, so instead of I mean, so imagine if you have used this in your design, 250 megapascal, instead of this value, then at least you can size up properly when using a much accurate value. Although again, as I have always said, that that depends upon, I mean, sometimes this is just incorporated in the safety factor. So how big is that safety factor? Anyway, how do we know, by the way, if the loading is a static loading or a dynamic loading? So that depends upon this equation. Okay, this time of applied loading, if it's greater than 3 tau, so this tau is the period of vibration, m is the mass, and k is the spring constant in what is this, Newton per meter. Okay, so we have this condition to be able to determine if the loading is static or it is dynamic. Okay, so the next topic is the equilibrium equations, and you have encountered this many times already. It just simply means that, I mean, equilibrium condition just simply means that the body, or the material is not accelerating. Okay, so that means that the summation of forces and the moments, they are just zero, and these are applicable in the I mean, if we use this rectangular coordinate system, so the x, y, z. So the summation of forces in x, in y and z, they are zero. The summation of moments in x, y, and z, they are also zero. Now, if in case the problem involves motion, so we will use these equations of motion, and that's simply the summation of this one. Summation of forces is equal to mass times acceleration. So if the force here is or the forces here in this side, or the forces acting in the material, they're not balanced. If there's a resultant force or something, then that will cause acceleration of um, of the the material. Okay, and by the way, even though let's say we have a shaft, and this shaft is rotating at a constant speed. Okay, so even though this one is in motion, okay, even if this shaft is in motion, as long as or usually in mechanical systems, these are just this has constant velocity. Okay, so if the velocity is constant, then simply that acceleration is zero. Okay, because acceleration is simply delta v over delta t. Okay, so if there's no change in velocity, then this is 0. Okay, so going back for the equations of motions, we use this equation: summation of forces is equal to ma. And if we consider rotation, I mean the rigid body itself, or the material body, if the material itself is rotating while let's say while translating, then we need to, and if we need to take into account this rotation of the body. Okay, so for example, we have this body right here, this arbitrary body, and then instead of having that position, it's now something like this. So it rotated, right? So it rotated while translating. So if we need to take into account the rotation, then we need to use this equation, that the summation of moment is equal to I. That's this one is the mass moment of inertia. Okay, so this is the mass moment of inertia. This is not the area moment of inertia, but rather this is the mass moment of inertia. And this one, this alpha right here, that's the angular acceleration. Okay, so this one is rotation, this one is translation. Okay, so what else?